Save. All right, so we are officially recording. So we're at November the 1st, 2023. This is going to be our last official meeting of Geostats. So today, it's largely going to be lecture. I'm going to do a couple of demos, but we're not going to have a lot of hands-on things because I want to talk about geographically weighted regression. I want to talk about circumventing issues in geostatistics, and then talk about the final and what it's going to look like. So it's going to be a combination of some hands-on stuff, some extraction from tables, kind of like we did there. So a healthy combination of the hands-on and interpretation of the data, starting at quadrant analysis and point pattern analysis and moving forward. And so, as you can see right here, today we're going to talk about addressing ancillary issues. I'm going to do a short lecture on what we call geographically weighted regression. And then on geographically weighted regression, and then we'll talk about circumventing ancillary issues here in anticipation for the final that we'll give next week. I'll be out at a NASA conference in San Jose the following week, and so I think this will be a nice tie-in to a nice conclusion so that people working on the position paper or people who are taking this as an undergraduate class or taking this as a graduate class for graduate credit, or maybe potentially taking this as graduate class in the future, can do the position paper. And remember, for the position paper, I want everyone to utilize one of the skills that we cover in this class. Some sort of geostatistics, t-test, ANOVA, prove or disprove some type of hypothesis or disprove it. The one thing about this class is that if you don't prove your hypothesis, that's okay. If you were to say, I think COVID rates in July of 2020 are going to be statistically different between suburban, urban, and rural areas, and you find out they're statistically the same, you found out they're statistically the same. I think a lot of times people are off to prove these kind of big things, and not proving something is just as much of a research find as proving it. So, please if you find that there's no clustering of COVID rates or no clustering of income or whatever, don't find these associations, don't be too concerned. We've run a couple of papers where our hypotheses weren't proven, and actually it was proved to the opposite. And so those are some things we kind of get excited about. And so we've got those things going on right here, because we're going to talk about some of these maps. We're going to talk a little bit about geographically weighted regression, of which I'm not a super big fan, but we'll talk about it a little bit and we'll kind of go from there. So I'm going to talk a little bit about geographically weighted regression. It's basically it's doing OLS, ordinary least square analysis, and then I'll kind of show a little bit of a demo. We'll start talking, we'll have our break, finish my talk on ancillary issues, because a lot of times when you write a research paper, you're going to have a part called the discussion. And the discussion is, these are all the things that I could have done differently that might yield different results. And so when we start talking about those, or maybe after the break, I'll show you from my paper a couple of the discussions that we have, because there's going to be someone sitting in the back saying, did you think about this or think about that, or things like modifiable area unit problem or heteroscedasticity, and we'll kind of mention those issues there. And when we take data science next semester, if people take data science, I think we're going to get into a little bit more advanced stats where we kind of focus on OLS and focus on two-tailed t-tests, which are kind of my go-to statistics that I want to make sure equip people with those tools. But we have the idea of spatial dependence, because when we ran what we call OLS, ordinary least squares analysis, it's basically another word for regression. There's different forms of OLS. So we talked about kind of the true mathematical model for OLS, where basically we looked for factors that explained it using this whole y equals mx plus b, and then we expanded out to 2, 3, 4, 5, 6 dimensions, which are difficult to visualize. So we looked at all the factors that help explain distance to the nearest convenient store, age-graded cancer mortality rates, or whatever. But the one variable that we don't account for in OLS is geography. This is geostatistics class. And so we have the idea of spatial dependence, which talks about the existence of functional relationships between what happens at one point and what happens elsewhere. And so I think this builds upon a little bit of your clustering, but it creates a y equals mx plus b for every single enumeration unit instead of just one general one. Me, I don't want to say I'm not a super big fan of OL. I'm not a super big fan of what we call GWR. I've run it through both R, but it reflects spatial continuities of social processes which take together and help bind social space and to recognize whatever this means here. But we're going to kind of just look at the equation right there. And so it does that whole y equals mx plus b. So this is our standard regression formula, but there's another variable in here that takes into account location. So for every enumeration unit, you're going to have your own y equals mx plus b. That's pretty much it. And so we have all these different places. So we have our dependent variable and our independent variables. So y equals mx plus b, what explains the age-graded cancer mortality rate? That's your dependent variable, and everything else is your independent variable. The only thing that geographically weighted regression does, it also includes location as an independent variable that impacts our dependent variable. That's all it does. And so we've got all these lag predictors, and we can let other people kind of explain these here. But these local methods, we have local filtering and spatial dependence and all this nasty stuff. But what I really want to get to right here is it creates for each of these enumeration units, it creates its own separate y equals mx plus b. And I'm going to show a kind of a real brief example that we have existing statistical relationships and geostatistical relationships over space. And so the whole idea of non-statiarity, we've talked about this before. We have kernel functions, grid functions. And so when we run this, the one thing that geographically weighted regression does is that it gives you an independent R squared for each of these factors. Now, I want to put some people on the spot, maybe some people here too. What's an R squared give us? What's an R squared tell us? What's an R squared? Do we like high R squareds, low R squareds? What is the highest R squared that we can get, first of all? What's a good R squared? Let's pick on someone here. No, I'm not picking on anyone. I'm not in the picking on mood. All right, but R squared means if it's exactly on the line, y equals mx plus b, that we can predict one dependent variable with all the independent variables. Can we do that with 100% certainty using like social economic data? No. So we typically have R squareds like 0.3, 0.4, 0.5, 0.6, meaning if it's 0.6, we can explain 60% of it using our existing variables. And when we ran those examples, we were getting R squareds like 0.2. So we could explain cancer mortality rates using income and age and race and all those other things, but there's still a whole nother 80% of stuff that we can't explain. Now, what is that other 80%? Can someone explain what that other 80% is going to be? What are the other 80% account for that we can't model? What are things that are unique to you versus me versus Alondra versus Barbara versus Chantel versus Caitlin that we really can't quantify or are difficult to quantify? Genetic predisposition. I can't account for that in all this model. I just know how many people in my zip code have a certain income. Okay, my diet, other things like that. I can group it by spending patterns. And so today we're going to talk about things called ecological fallacy and exception fallacies next that are difficult to do. But when we run this model, we get a single y equals mx plus b, but in models like this right here, each of these separate counties gets a y equals mx plus b, so these R squareds are going to change. And if you remember, when we ran that OLS, we got a map of the z-scores, and the z-scores that were really high or really low just told us how far away our residual was. Okay, that residual, hey, these values have really high residuals, meaning they're higher than what they should be, or lower than what they should. Then you know what I'm saying. Okay, here you can see the model works a lot better in these darker counties as opposed to these lighter counties. Why? I'll let you all figure that stuff out. Okay. And so it gets a little bit more complex. When we run, we're talking just a little bit about chapter 12, and then we're going to hop into chapter 13. But when we run this thing here, illiteracy is explained by urban population and this percentage right here. And so the rest kind of works the same. Bandwidth method, number of neighbors, weights. I rarely use weights right here, but you can see we get things like R squared, 0.54. Okay. And so now I can predict these using, what is the percentage rate here? The number of standard deviations we're away from things here. And so that's a real quick instance there of geographically weighted regression here. I kind of ran this tool because I'm going to harken back to this later. But I ran this for standardized residuals and this is the output, because at the end of the day, we want to run this output right here. And what I tried to do was I tried to explain age-graded female cancer mortality rates based on income, poverty, access to food, green space, which is an environmental indicator, percentage of SNAP recipients, and percent minority. And I got a map that kind of looked like this. And when I ran this thing here, you can see, all the way over here, I get some sort of R squared. I swear, a local R squared. And we're looking at really, really low R squareds, which means that we're going from like 0.8 all the way down to 0.0, meaning that I can only explain age-graded cancer mortality rates using only about 10% of these indicators at best. At best. And so you can see all this other stuff that explains it. We've got our residuals, and then we have our variables, basically our coefficients for each of these other variables right here. But these R squareds are kind of not very good. Okay. There's so many other factors here that explain it, but you can see these changeovers place in space where that the other ones do not. So that's about it with geographically weighted regression. All right, now I'm going to talk about circumventing issues in geostatistics. And the one thing I'm going to mention, when you write a research paper, and this is a paper that we wrote for a journal article, and hopefully we're looking towards that, we developed a new raster-based metric to measure food availability, relative food availability in rural areas. And so this is an article that me, Dr. McGinn, a couple of other folks here wrote. Okay, and we used a raster-based metric here. You can see the percentages. What do I care about? I just want to look at the maps. Okay, maps. Here's some maps right here. Maps right here. Maps right here. Go down here. But what I kind of did down at the bottom here with my results, t-test results, and this should be in the modules, and then we'll kind of look at these a little bit too. But we have something here in the discussion. Okay? Discussion, basically, we have to go through and explain all the things that could have been done differently. And you see a little bit over here on the left here, we're going to talk about something called MUP, modifiable error unit problem, meaning that, hey, we've got reliable data, margins of error. I've talked about the idea of margins of error, right? If we're using smaller sample sizes, we're going to have bigger margins of error. And like I said before, I said, hey, if I'm going to make some assumption or make some statement that says, all NCCU faculty are statistically taller than all NCCU students, I just did me versus her, I'm going to win. I'm going to prove my point. But there's only a sample size of 1. So if we increase our sample size, that margin of error is going to change. We bring in Benjamin, who's going to be taller than me, or whoever, and we average those out versus a sample size of students. And so we have this discussion right here. And then we have our census block groups. And so I kind of go through and explain some of the things that could be done differently. So what we're going to talk about today is how we kind of circumvent some of those issues. What do we do? What are those issues that you run into that someone in the back of the room is going to say, hey, have you thought about this? And so when we look at processes, patterns, and analysis, we're operating in space that we create patterns. So we have these different processes and we have these different patterns. Because when we look at these, to be honest with you, it just looks like a bunch of dots there. And so we're getting to a point in time where there's this arms race between processing speeds and storage space, where that, and especially with the cloud right now, that we have trouble accessing the data that we can do everything to in an appropriate time. And so with spatial analysis, we want to identify and describe the pattern and identify and understand the process. And a lot of times I tell people, and I was talking to a class today, that I'm like the where person. In this class, we talk a lot about the technology so that we can stick stuff on a map and maybe describe the patterns. And we're hopefully getting to a point in time where we have some PhD students in this class and some real forward-thinking researchers to understand the why on these things. Why are suicide rates high in this part of the state, or AIDS mortality higher in this part of the state, or COVID or SIDS deaths in certain parts of the state? Because I'm just the where geek. I focus on the technology so we can do that. Because to be honest with you, maps are good. We love maps. And like I said before, when I worked with the military, they always thought of me as like the map guy. You can just go through and make maps, but I'm a lot more than the map guy. We can facilitate data-driven decision-making, prove or disprove hypotheses, and do all these other neat things here. And so we can look at something like this on the left or the right. Which one's more clustered than the other? Can you tell with your eyeballs? Can't. And so with the quantitative revolution in like the 1950s and 1960s, where geography evolved from more qualitative, like descriptions and capitals and superlatives, to something where we can analyze this, to now in the 21st century where we can click a button and run this thing and run a nearest neighbor analysis or nearest neighbor index to calculate what's the average distance from each point to the nearest neighbor and calculate that versus a random distribution of points. Just think about how far we've evolved. Now, I think a lot about it because, when I first started doing GIS, I was doing stuff like command line stuff, and these days we just got nice little buttons that we can click on. Back in the day, I thought I was real good at GIS, really good. Now I know how much I don't know, because now we got cloud. We got all these phone apps that we can do. We've got Benjamin working on surveys. We got Benjamin, there's a whole field of just collecting surveys and matching these up with GPS units. And you won't need a GPS unit because your phone will be close enough. But a whole field of surveys and tracking applications, as well as remote sensing is anyone taking remote sensing this semester? Oh, you are? How's that going? Good. Because why is this important? Is this clustered? Because we need to measure and test and not guess. And I like using the word statistical significance with these, because those clusters, those red polygons or points that pop up, have been shown to be clustered with statistical significance. Those t-tests and the results of those t-tests that pop out from Excel are the results of tests with statistical significance, where we look at 90 and 95 and 99 and that E13, those things are going to be statistically significant. And to me, we've gotten to a point with tools that we look at in Excel, and you can extend these to R. And our data science class next semester, we're going to do a little introduction to R, the part of R that I know, and you'll kind of be introduced to some of the things that I do with data science and data wrangling and other things, and how we could turn this into kind of quantifiable data that we can measure with statistical significance, because this is science. We make a hypothesis, and then this is how Earth management decisions are made. This is how we match up, air quality versus poverty. When we make these kind of big ticket statements like poverty rates are higher in rural areas compared to urban areas. This is where kind of the rubber meets the proverbial road so that we can prove these with statistical significance. Now, there's a lot of leeway because what's the definition of urban and rural and all these other things there? There's 9 different definitions of urban and rural. So I'm going to talk about all of these things here. Where are there places where you can change your results? Just the whole definition of urban and rural. Does anyone remember what the definition of urban and rural that we used in this class was when we were doing that two-tailed t-test or ANOVA with COVID rates? James, I think James, he was joining us at the time. He said anything more than 15 miles is rural, everything less is urban. Is that going to be your definition? No. So you might get different results. She might say 20 miles. Jayla might say 20 miles. You might say 25 miles. I might look at population density, anything with over 1,000 people per square mile for the zip code, because that's one of the definitions of urban according to the census. Or we've got counties that are designated as urban or metropolitan, micropolitan, or rural. So I might just go with the county level definition. So we're going to talk about outliers, especially for the Geostats org, data sources, data extraction, things called logical consistency, scales, enumeration, the whole idea of MAUP, modifiable area unit problem, sample sizes, small number of problems, the methods applied to data. And these are all things in those input parameters, when we just click next, 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 these are all the things that we can change or we can think about. Residual mapping, use of variables used in regression, variables that are inverses, variables that are two alike. And this is a big fancy word called multicollinearity. And, Dr. McGinn, he kind of tells his story when he was working on his thesis in 2012. I think it was 2012. And he was finishing it up, and he finished his thesis up in like Super Bowl weekend. Super Bowl's in February. And yeah, he finished it up in February. You know what I mean? And he spent the whole rest of the semester kind of tidying everything up because our semester ends. I'm going to be gone in 2 weeks, and I still have not received any theses for this semester, and it's like November 1st. So I'm getting I get real emotional about that stuff. I'm looking at all the graduate students and potential graduate students there. You too. You know what I'm trying to say, right? Get your stuff in early because I'm going to California in a couple of weeks and I'm not going to be kind of reading people's stuff while I'm there. But all kidding aside was that he was, working on this and his advisor said, hey, we need to kind of look at some of these things with regression. And so he went through and did something called stepwise regression, which kind of goes in, pulls and pulls out, uses algorithms to kind of get rid of certain variables used in regression. So he had to go through and explain heteroscedasticity, kurtosis, and skewness, and all these other things that we're going to mention here a little bit. Now, the first thing we look at here is the use of outliers. Okay, remember Geostats org. What's the definition of high and low? This is kind of what we have here. Definition of high and low. What is it? What is the definition of high? Above the mean and below the mean, exactly. And so if you have some outliers attached to these with normalized age death rates, and when we ran this, and I'll show you an example right here. I got rid of when I ran this with our PhD student, we had 763 zip codes, but I got rid of all the zip codes with a population less than 500. And you're kind of asking me why. And we can see why, where that I had the mean of the data set for all 763 to be 4.6. I got rid of them, and it's 4.3. So we went from 4.6 to 4.3 just by eliminating less than 50 zip codes. What do you think was in those 50 zip codes? There was an outlier. And there was one, and these age-graded rates were like 2, 3, 4, 5, 6, 7, and there was one that was 272. So what do you think that does to the mean? It pops it up. And what does that make the definition of high? it pops it up. So there's not going to be a lot of high values because we have this tremendous outlier. And so when I ran on this original data, I ran this hotspot analysis. Look what I've had here. What do you think? What do you think someone at a journal article, or what do you think I'm going to say when you run this? What do you think I'm going to say? This is not much of a hotspot map, is it? You know, and all kidding aside, why? Because it's centered right on that hotspot that had a value of 272, and it might have been surrounded by a couple high ones. Now, it might be really interesting why that is 272, but if I remember right, the population of that was really, really low and maybe only had 30 or 40 people, and 3 of them maybe died, 2 or 3 of them maybe died of cancer. So what's that do to the rate? Moves it way, way up. Or when we age graded it, it might have had 1 person under the age of 20 or age 20 to 40, because we age graded have die of cancer. So that's going to pop things really, really far up, because remember, when we age grade, we basically weight by the proportion of people within certain age cohorts. So even though we had lots of deaths age 80 and over, there's not a lot of population age 80 and over. So when we age graded, it kind of got rid of those. So, but when I look at something like this, you can see not much going on here. I get rid of it. I just get rid of those 48. Look what we have as for clusters right there. And we're going to actually look at some other types of these clusters here in a second when we finish up here. But just by getting rid of these, I go from this to this using the same exact algorithm. Why? Because I just went through and got rid of these really, really high values, the outliers, which change the definition of high. Change the definition of high. And so when we ran this originally, we're like, no journal's going to like this. No one's going to like this. Okay, what's the problem here? All right, we see values like 15, 20, 2, 3, 4, 5, and then we see 272. That's going to move that thing up. That's going to move that average up significantly. So these are some of the things that we have. The other thing, data sources are a source of error. Now we have something called logical consistency. The idea of logical consistency is that data received from different sources should be consistent in both structure, coverage, and kind of probably collection method as well. I've talked before in my 34-35 class where that if I look at crime data for Durham, it's got like 30,000 crimes. I look at crime data for Winston-Salem, it's got about 60,000 points. Does Winston-Salem have twice as much crime as Durham, even though they're about the same size? No. The way they collect their data is slightly different. Over here in Durham, they use something called UCR, Uniform Crime Reporting Standard, as opposed to UPCR, as opposed to something called NIBRS, National Incident-Based Reporting Standard. So over there, if they have a homicide and a robbery and a assault all at the same time, that counts as 3 incidents. Over here, that counts as 1 incident where they take the worst. So even consistency among collection methods is going to be really different. Now, other thing we'll talk about is the different collection sources should be consistent both spatially and temporally. So if we're mapping age-graded raw mortality rates versus raw data, if we get data from the sheriff's office versus the city crime data versus the open data site, and I think in my external links, I've provided the link to the Open Durham site, so you can download Durham Crime, Durham City Crime, Sheriff's Office, and if you just look at the attributes, you'll notice that the attributes are different for crime from the same exact county. And so this is an example of some data collected from the Durham Sheriff's Office. This is data collected from the city office. And so starting to combine these together, it's going to be hard to make some sense of these because the collection methods are going to be slightly different, as well as the attributes. So we have something called the charge description out here, which may not equate to a charge description here within the city. And so we can look at this crime data versus this crime data, which are going to be very different from each other. Okay, that's another of the issues that we run into. Another thing we run into is what we call edge effects. I think we talked about this before, but when we run things like density analysis, quadrant analysis, they should only include where there's full coverage of points. Now this starts to become a little problematic, especially if we run along the north edge of North Carolina. How do we circumvent those? So study area should only include a buffer when running analysis that may include areas outside of the study area, but you might not have available data. So this is an example of what we did with our quadrant analysis, where that my study area is this 9-county region, but I included a buffer all the way around where we were looking to access the vegetable markets, because in theory, someone who lives in this part of the study area may frequent this vegetable market and travel outside of the study area. So remember what you did last week with that density analysis. It had a cell right there, and it looked for a certain distance around that cell. Now, did you tell that cell that it had to be within the study area? We could set up a mask that only displays it within the study area. Or we could set up a processing extent, and that gets a little weird at times. But you're also working with what? You're also working with deer vehicle collisions for the state of North Carolina. So what do you think is going to happen at all those edges? You're going to have some problems there, aren't you? Because you're in the middle of the state. What's happening? You're looking at all the points around you. There's enough points around you. You're looking at those edges. It's not counting the points in Virginia. Why? Well, there's no points, and we don't have any points for Virginia. And so those are some things to think about and how we circumvent those. But you see here, we included as part of our processing extent these points right here because, well, they might be part of the study area. So we run some density analysis or quadrant analysis or whatever, and so we can create our quadrants for the entire study area plus the buffer. And we have full coverage of points, so when we run the spatial join, it allows us to do that. Also, the size and shapes of these enumeration units are also important. So you can see here, these are deer vehicle collisions, and I think I mentioned this before, for this 3-county area right here. And you notice I included all a nice little boundary around these. So when I run density analysis right there, we don't have any discontinuity right here. You don't see these low values, low values, low values, low values, because I've included the points outside. And so I set up a processing extent to be for the entire state, but then I set a mask. Okay, remember we set those last week? We had processing extent and mask to be for just these 3 counties. And then now here I could run my density by quadrant right here. You know, these density by quadrants get a little weird right here and these areas right here. And so I might have included those points or maybe not. The other thing we have, and I mentioned this word before, it's called MAUP, Modifiable Area Unit Problem. It's statistical bias based on the size and shape of enumeration units. Now, previously, why do we use quadrants? Why do we use these squares? Why did I go through the trouble of creating them?
Because we need to certain analysis needs to be squares. So
yeah. Squares, they're not biased, right? They're not ones, they're all the same size, right? Let's forget about these ones at the edges here, but they're all the same size. So if I know how many are in this, then I can easily calculate the density. So I know everything in blue, since it has more, it's got a higher density. I don't need to normalize or anything like that with these. And so we have something called MAUP, Modifiable Area Unit Problem, where that I have 4 points right here, 4 D vehicle collisions. Depends on how I group the points. So if I use perfect squares, I've got 1 in each. If I've got these kind of rectangular, I've got a 0, a 2, a 2, a 0, where that if I group them this way, now this way is how reality really looks in terms of census tracts and block groups and all those other things, where that now I've got this really big block groupers that includes all 4, and I've got a couple of zeros. This is really, unfortunately, what we deal with, but we like dealing with this thing all the way on the left. Now, we have natural phenomena like deer vehicle collisions. I can count these by squares, but in reality, do I collect data by squares? In what units do I store population and median household income. What units do we work with? Counties and zip codes and census tracts and all those things. And those census tracts aren't squares, they are block groups, and they take on weird shapes, and they're literal in shape, Littoral, out near the coast. And so when we combine these smaller results, we might get different results. We might get, hey, here's our cluster right here, where that here, there's no cluster whatsoever, even though they're all in the same quote unquote location. So these are important as well. And so when we start to combine things into different units, if we go from, our zip codes right here to quadrants right here, we might get different associations between, water age and illness rate and water age and illness rate here. These are two entirely different things here. Even though it's the same exact points, just superimposed on a different type of map. This is an interesting one here. And so a lot of times you'll see the word modifiable area unit problem right here. This is taken from one of the papers. And so after our break, I'll just show people where those papers are. But basically what I did was, and I might have shown it right here, is that I group data at the block group level, and then I run a two-tailed t-test, and then I run another two-tailed t-test with it at the tract level and say, see, these indicators popped at both the pops meaning statistically significant at the tract level as well as the block group level for median household income, percent minority, and high percent Hispanic or something like that. And so they popped at both of these levels. So see, it's not a MOP issue. It's basically the underlying theme that we were trying to prove with food access or whatever here. And so you can kind of see these right here. And so you can pull some of these from my paper because under week 13, I've posted a whole lot of papers that we can look at. Here's one thing, and like I mentioned before, now I can superimpose quadrants on top, but now I've got block groups. I've got these bigger quadrants right here. I've got these tracks right here. Which one's the best? Either. That's a whole field of study that you want to do here. If people want to get into it, we can superimpose these kind of points on top of these. Now, something like this here, these are pretty good because why? We got population counts for these. These are pretty good right here, these squares, because we can just kind of count these and do a nice spatial join and count these. But we don't have, I don't know how many people live within there. Can you count how many people live in here? Is there any way to estimate how many people live in this square right here? I'm getting deep here. You have any ideas, Benjamin?
I mean, it seems like a lot more work than it'd be worth.
A lot more work than it'd be worth. And basically, you would have to kind of take the population pull the population densities from each of the census tracts that intersect, and then calculate the area times the population density within each. So you'd kind of run a combination of some intersect and some summary statistics, and then some joins to figure out the total number of people based on the population density. And so it's sometimes difficult going between these kind of census-defined units and these other quadrant units. Now, these quadrants are nice and neat because, well, deer don't really care about census tracts. They don't. And other things like highway miles and land cover and all those other things don't care about census tracts, where that populations and other things do, which we collect data. And so sometimes those are kind of problematic. But when we look at things like census tracts versus zip codes, we can look at things like our standard deviation ellipses, which might change. And this kind of goes back to week 4, 5, 6. And so these things might look extremely different depending upon where you collect those data from. Other thing we deal with, sample size. Like I said before, I can prove a statement or say, hey, NCCU faculty are all taller than the average student or whatever, and I can do one sample, but it's not going to work. And so we have things with margins of error. And a lot of times when you download data from the census, you get information about margin of error. I think I still have it right here. I might. Okay. But I just downloaded some census right here, downloaded some data from the census. I'll look at documents, downloads. Here it is. Nope. Here it is. I went and downloaded some data from the census. I think we were looking at like poverty rates or educational attainment for all the zip codes in the state of North Carolina. And so I went to this place called CEDSI. It's called Data Science, Center for Data Science. But when you download data from the census, this is what it looks like. And so I've got these zip codes right here, and I've got tons and tons of attributes. Okay, so I have the estimate of age aged 14 to 24 with less than a high school graduate. Here, I've got the estimate total population of age 18 to 24. So if I divide this column divided by this column, or rather this column divided by this column, I can get the percentage of people age 18 to 24 that do not have a high school diploma, right? That makes sense. Now, look at these right here. This is the margin of error. So this zip code actually has 940, but it could be all the way up to 940 plus 283, or 940 minus 283, age 18 to 24. So a lot of times when we download these data, we get these margins of error right here. Now, some of these aren't too bad, like 86 plus or minus 9, but 213 plus or minus 203. So it could be 10, it could be 416 just for this zip code right here. And so the census does a really good job of kind of keeping track of these kind of margins of error that we look at. Because this margin of error, do I say plus or minus 3%, plus or minus 5%? I could calculate those percentages. And we're going to be seeing a lot of that in the upcoming months with elections and all that other stuff. Or we can calculate using those true numbers right there. And so a lot of times we've got these big nasty formulas right here. Z squared times p hat, 1 minus p hat. Forget about this stuff here, but when I have a sample size of 100, our margin of error is plus or minus 14, just using this formula alone. Okay, sample size of 1,000 plus or minus 4%. And so now if I were to get 1,000 faculty versus 1,000 students, my margin of error is going to be about 4%. Essentially, kind of, I don't want to convert the p-values of the z-scores, but they should be within about 4% of each other. 4% of each other, but I get 10,000, that margin of error is like plus or minus 1%. And so these are the things that we see when you look at elections and they say they want this candidate, 38% plus or minus 2%. This is the formula that we're kind of basing it on right here. And it's just we convert it to a margin of error because who wants to look at this stuff? Not me. I want to look at these things right here. Other thing we run into, small number problem. This is some information. These are some data from the North Carolina Vital Statistics Database about infant mortality rates. Okay, infant mortality rates right here. And so a lot of times you might see a star right here or 0 values right here where we see really, really high infant mortality rates right here. We look at this here and we see a rate of 400 for every 1,000. That's a really, really high infant mortality rate. I think we can kind of look at some others right here. We can look at some others right here. This one right here, which is 1,000. Get that one out of the way right there. But when we look at these infant mortality rates, we can look at extremely high infant mortality rates, like right here. It's basically, you have a 40% chance of having an infant mortality in this county right here if you're a non-Hispanic other infant death. What's non-Hispanic other mean? I got class, yeah.
What time is it?
7:30. Yeah. You can. Yeah, I was here all day here, so yeah, I was here all day, so I was kind of waiting for you. Yeah, yeah, yeah. I had a couple classes and stuff like that, but I was. Yeah, I'll be on campus all day tomorrow. Yeah, yeah. I'll be on starting about 8:30. So, what does other mean? It means not white, not African American, not Indian. What else is there? Hawaiian Pacific, Native Islander, whatever. So we could say, are there a lot of others in Anson County? Probably not. And so we run into these really, really high rates here, extremely high. And so you'll see a lot of these for non-Hispanic white or non-Hispanic African American or things like that here, like Bertie County. These are extraordinarily high. We go from 1 to 2 to 3 to 4, and we got these big differences where we have these other counties here where they're not going to pop quite as much. Okay, so be aware of those small number problems. If I go from 90 to 180, that's a big problem. If I go from 1 to 2, not as big of a problem, even though the rates are going to double going from 1 to 2, where we calculated those percent changes. So that's something else to be aware of too, that small number problem. And so remember when we did that in change detection analysis, well, we had 300% increase. Well, we were just going from 1 year to the next. It went from 8 to 24 or 2 to 6. Yeah, that's a lot, but I'd be more concerned if it went from 40 deaths to 120 deaths. So be aware of those. And you notice there's some real stipulations up here, real stipulations up here. And it's really good in that it explains it pretty well. It explains this small number problem and says, don't do this. We've got the small area problem. Changes in values for areas will change normalized density measures and affect discontinuity. Okay, this is a map of New Jersey for what we call townships. Up in New Jersey, basically all counties are subdivided into towns, cities, and townships. And so I lived in this kind of little township right there. It was about 40 square miles, but these are the subdivisions of them, at which we collect all data. And you can see the year that black bear encroached on these areas. So where I was growing up, it was 1995. By 2000, they had gone all the way to these. By 2009, had encroached on the entire state. So in this instance, like black bear are kind of invading the whole state. Now, why are they invading? Because there's more people there that leave food out that people go out and eat. The bears go out and eat. Now, the problem is here, we see all these little dots right here. Why are these dots kind of speckled throughout these red areas here? Why don't they have any bear sightings here? Why are these little towns, why do you think these little towns not have any bear sightings? What is your best guess? They're really, really small. So what are the chances that a bear happens to show up here as opposed to this whole area right here? Not as much. Now, how do we circumvent this? What did I do? I created a quadrant map here. So I created a nice quadrant map so all the areas of everything were all the same size. So I think in an instance like this, quadrant map would be really good because this, you're kind of saying, hey, there's no bear here, but there's bear all around. Yeah, bear probably walked by here, but they just didn't happen to be seen in this tiny little, half mile by half mile town or township. Other things we've got here, we've got something called residual mapping. Now, residuals are going to be the actual minus the predicted. And so when we run a y equals mx plus b, we run regression in Excel or we run OLS. In ArcGIS Pro, we can map the residuals. And so when we map the residuals, there should be an even distribution of points about both sides of the residuals. There should be. And people like me aren't going to care, but people who are really care about statistics are going to care. Okay. And this will be kind of the last thing we'll talk about before the break here. We'll take probably about a 10-minute break. I'll finish talking there, and then we'll kind of talk about the final, and I'll actually show the example and some things here after our break. But we also look at the relationship between different variables, the idea of multicollinearity, where that independent variables should not be correlated. And so what Dr. McGinn did for his dissertation, where he ran something called stepwise regression through a program called SPSS, which we all have access to through Eagle Apps. We did stepwise regression where it said, hey, are these two variables related to each other? Because we can keep the variable, eliminate one of the variables, and look at stepwise regression. Because if I were looking at something like COVID rates versus race, and I said, let me look at the percent minority versus the percent white, they have a one-to-one relationship with each other. And so if I were seeing if there was any relationship between COVID and white or COVID and minority and use those as explanatory variables, basically they're going to cancel each other out because one is just 100 minus the other. You know? So those things, kind of stepwise regression is really good about making sure that two variables aren't related to each other. Because if I were to look at percent minority and white, basically I'm going to get an R squared equal 1 because one is entirely dependent on the other. It's just 100 minus the other. That's a negative correlation as percent minority increases. But how do I know it's an R squared equals to 1? Because it's all on a line. It's all going to be on a line. That's what we want in real life, you know. We'd be able to explain something with 100% certainty, but we know in environmental and sociological and all these other types of research that isn't necessarily the case. All right. So we'll take about a 10-minute break here. We'll meet back here about 6:02. I'll finish talking here. I'll kind of bust out some of my examples right here. I'll show some references to my papers, and then we will talk about the final. And so hopefully we'll be out of here before 8:30. So
Did you get my email with my surveys?
yes, but I didn't answer you because I was gone all Friday. So
Okay. Did you get a chance to look at them?
You sent me a link to them, right?
Yeah, it should have been 2 links, and I sent you a Word doc with like my notes and stuff.
Okay.
Some additional context.
I'm gonna say it's probably gonna be fine because you are gonna be fine.
Hopefully you're able to view them.
Survey 1,
Yeah.
store name, store address. So this is only gonna be answered once, right? Okay. And then this survey 2. Now, what I would do here under survey name, store name, is have a drop down.
So there's a reason I'm not doing that.
Okay.
And I thought about it.
All right.
If this database precedes me, if it goes
Beyond?
used beyond my involvement in it, I wanted it to be adaptable. So the join feature is going to be the address. The address is going to be the join feature.
Okay.
And
What if I type in a different address?
so that's why I got under the little instructions there. Important, make sure the address matches the correct address on instructions.
Okay.
So I've got a stipulation there, and I wanted it to be. So right now we got 20 stores,
Okay.
10 grocery stores, and 10 mini marts and convenience stores. It does not span every store in Durham, and it doesn't have any repeats.
Okay.
So I wanted the survey to be adaptable. So if we get 2 or 3 more people on here, we get more manpower, we may be able to do all of Durham County, either every store, or basically I didn't want to have to make a new survey if we're changing where we were observing. We could just add on.
Okay. It would be neat if we had it would be neat if we had a drop down of all the stores. And that was dynamic. So when you added a new store here, it would be added to that survey too.
That would be interesting, but I don't know how to do that.
Well, maybe
can look it up. But
Okay, good. That's what I was waiting for you to say. See if we could do that. If not, I wouldn't give it too much. You know, you might have to get into some arcade and stuff like that, doing some things on the back end.
and that, yeah, that sounds like, because it didn't seem there was any prompting when I was going through all the options and stuff. Because whenever you edit a survey, it changes.
Oh, that's right. Okay, you can't edit a survey
Once it's been published.
once it's been published. Oh, that's right.
So yeah, because that's what I was thinking, and like if you could do that, that'd be great. But
Yeah.
that would involve editing the survey.
After it's been published. Okay.
So I was thinking probably I mean, it's not super neat, but probably the most effective way is just to have a Word document or a notepad document that just has, these are all the stores, these are all the addresses.
Okay.
That's your drop down.
Okay.
And so that way, you know, you're able to get, there's additional instructions, which makes it a little bit more complicated, but I think it works this way.
Okay. And the one thing about it is that when we finish up our thesis, you know, when you finish, not we, you finish up your thesis and you're like, what are things that I could have done differently? Then this could be one of the things that said, all right, now they have you editable elements that you could change or update or whatever. So, and those would be one of the things in the discussion that you can talk about. So,
These are all the stored.
oh, cool. All right. All right, neat. I like this. This is impressive. It looks like you've put a lot of thought into this.
Yeah, it's a lot of thinking in the first month. So
Yeah. So you don't go back and redo or redundant because
I like thinking about things for a long time and then doing it right once.
Okay.
That's my method. So
all right, when are you gonna start collecting data?
as soon as you're ready for me, I can.
You can start ASAP. I'd like to see some stuff. I'd like to see what happens over kind of holidays as we lead into that. Did you get a check this month?
For October or November?
November.
It's November 1st, so I haven't. Oh no, a check. I haven't checked.
Okay.
I haven't checked my check.
Because I'm pretty sure they processed everything. If it's next month, you'd probably you'd get two of the months. So I think I had it starting
I
in
have direct
October.
deposit set up. Would it be just sent straight to my bank, or would
Yeah.
it be?
Yeah, everything. I used to have students that wanted like checks, and I was like, we have to do direct deposit here. And I've had students that don't believe in direct deposit, and it's a problem.
I mean, I would prefer a check.
I
understand the need.
oh, I know the need. Yeah, I'm well.
But yeah, I'll go ahead and start collecting data.
All right, cool. I'm interested to see what it looks like too.
Yeah, me too. Yeah, I think I'll be using the web-based ArcGIS
Okay.
to display it.
Okay, no, that's fine.
Because I think it'll save me from having to download and re-upload. So
Yeah.
upload
Oh, it's gonna end up on the cloud anyway, so.
Well, I'll just do everything through there because I think it should have all the tools that I need.
Mm-hmm.
Yeah, so that's what I'll be doing in November then. Oh, but yeah, you can the staples I'll be observing was I had all those
Yeah, I saw the pound of meat, bananas.
like reasonings and stuff for them too.
Okay.
I believe the reasonings were in the notes. But
Okay.
if you had any questions about those, I can let you know.
No, I'm gonna trust you and just, my main thing I get emotional about is just consistency,
Yeah.
just maintaining consistency. So, but good, exactly. Cheapest. Yeah. Perfect. Yeah.
Yeah. So most of the regulations and the way that I chose these is actually based off of the WIC program.
Okay.
So what WIC approves as a staple food is where I got most of this. So, and that includes the sizes. So a peanut butter jar of at least 16 to 18 ounces
Okay.
That's approved by WIC. I used the 3 banana or a pound of bananas one that you suggested. Gallons of milk, the bread, WIC actually only pays for whole grain.
Oh, wow. I didn't know that.
Yeah, so basically, if there's no whole grain, then you're gonna record white bread, but if there is whole grain, it's the cheapest whole grain. So, yeah.
This is good. You put a lot more detail into this than I would have, but you probably have a little more time on your
Yeah,
hands.
my design goal was make it as if I'm not the one doing it. That was my idea.
Oh, cool.
That's kind of that's how I made it.
And does this thing look good on your phone?
Oh, yeah.
Okay,
That
cool.
worked great. Yeah, everything's readable, everything's legible, it's very clear.
Yeah, and we don't have to worry too much about the address because when we start doing the analysis, what I would envision is exporting it all out. At least have the address once, but exporting it all out in. Because if I'm not mistaken, if you're at the store collecting the information, it'll collect the XY with it, right?
I didn't set it up that way. I set it up to record the geospatial data of the address that you enter.
Okay.
Yes.
All right. Oh, that works too then. Okay.
So
You just need to be exact with that address.
Yes.
Okay, and that'll just be superimposed on itself every time.
Yep.
Or you can run a summary on all those for each of the statistics. And you're gonna get a lot of data, so there's a lot of different directions you can go with this. All right, let me take a quick walk around here and I'll open up the course modules, talk about some of these, and then we will be set. Are you getting the hang of this here? You're almost done here. Sounds like you had a rough semester here, so.
I wanted to ask you, for classes.
You just want to take all the classes we're offering?
I was gonna ask, so like, what's the plan classes that are
Oh.
on next day?
Data science is the one I'm offering, and it's basically kind of how to do some development, do an extension of this. I think it's, what are you taking right now?
Atmosphere and
Okay. It's just the data science, and you think you can take 2 classes or 3?
I think I don't know. Cause my job is doing some crazy stuff right now. So
I'll take 2, and what I'm gonna recommend is that you send me up for independent study as a 3rd class so that we can give you tuition.
Okay.
So you don't have to worry about tuition, and we'll give you like, working in $100 a month. So that'll just cover you. Based on food and others. So you can be registered for a full 90 credit, only take 6. And we registered for me under those, and maybe you could add one for thesis or project, maybe you can start working on that.
what do I have to tell you about pieces of like style?
Yeah. And you can do a thesis or a project. The project is usually a little bit more when you're clicking. Only about a third of our students do a thesis. And so, if you're working full time, I would suggest a project. So it's it's a little bit shorter than a thesis. A thesis is a little more 40 days. Most people I kind of recommend.
Okay, and so I think the lithosphere and movement class is kind of like part of the first part of the. This is part of the geosphere part of the. Which classes are part of the environment?
Environmental. Next semester we are teaching the science of climate change. That's one of the classes. So you might want to take that one too. It's a little more math heavy than, a little math heavy like this one. I don't know, is this class math heavy?
No, it was more math than the lithosphere.
Okay, she has more math than that. What do we do here? Pointing and clicking?
Yeah, it's like with the computer. The computer does most of the math.
Okay, we just have to interpret it.
Yeah, and then there we have to like formulas and writing it all out.
Oh, okay, yeah. So, yeah, and I think my data science class is gonna be kind of programming and things like that. I think the other class is atmospheric dynamics, so that's one of the core classes. I'll have to double check, but we'll check right now, those students. We'll get started in a second here. I'm just checking something for Jayla. And we will get started. Okay. I'm just looking at our core classes here because I kind of want to know now what we're offering next semester since I am the graduate coordinator. All right, class search. Spring. All right. So, atmospheric dynamics, science of climate change. The one thing, atmospheric dynamics is a core class. So I'd suggest taking that and then one of these two, me or Dr. Yang. So whichever one you want. And then I'll ask Dr. McGinn to add a section of independent study and directed research that you can take under me to get the full complement of 9 credits. And I'll work on him with that.
And then I just go register myself, or do I?
You can, yeah. You should have a pin. Otherwise, I got a pin. I think I got a pin, but I'll give you the pin for you to sign up. If not, Dr. McGinn has kind of a back door, so he can sign you up as well.
And when is that due?
I'll probably send some nasty gram to everyone. Have everything registered by, once you get those, you could. But if I remember tomorrow, I'll send you your pin so you can get registered. Okay. I won't be offended if you don't take data science. Either one of these will be good. And then Dr. McGinn might take a day or two to get all the other sections of things up there too. Usually there'll be like 10 classes listed, but these will be the face-to-face ones. All right. So, okay, we're ready here. We're talking about week number 13. Talking about week number 13. And if you look at week number 13, I've posted some of the papers that I've done in the past. And you'll notice most of these are going to have, most of these are going to look like, research papers. This is one that I liked here. Definition of the term rural. This is association. This is one, my wife was taking a class at Guilford College, and we started doing this, and we used purely statistical analysis, and I think this was one of the papers that we had before. But if you start looking at these things down towards the bottom, I start to put these things called discussions. And so you can start to see things like, while this analysis was comprehensive, it basically noted how distance can be relative in various ways. And so here, when we talk about food deserts, right here, it says 1 mile in urban areas, 10 mile in rural regions. And so at the end of the day in GIS, it's the quantification or the abstraction of maybe qualitative terms into quantitative criteria. And that's the one thing that I like doing in this class as opposed to other classes that we turn qualitative to quantitative. And so we use the USDA definition. And so we said 1 mile, 10 miles. However, USDA uses other definitions like 0.5 miles and 20 miles. So these are some of the things that we kind of talk about in the discussion, meaning I use 1 mile and 10 miles, but other people use other definitions. Here's another one. Distance is a valuable way. Typically, in this analysis, the application of the word rural. Other classifications of the word rural exist. And so, what's the definition of rural? Because basically, if you remember that paper that we did at the beginning of the semester, where basically we did two-tailed t-tests between food access in rural areas. And we focused specifically on rural areas where that we saw Black and African American and Native American rates were extremely high in the low access, low income areas compared to white counterparts, where we saw no statistical differences. And so we know these kind of marginalized communities, which are already marginalized to begin with, had poor access to food. beyond random chance. That's what that two-tailed t-test basically tells us. And so over here, it kind of talks about what's the definition of rural, because at some point in time I said up in the top here, these are your number of rural census tracts right here. The number of rural census tracts, we've got 716 metropolitan, 120 micropolitan, 70, and this is for low access. We've got about 2,300 total tracts right here that are broken down by metropolitan, micropolitan, and rural all the way up at the top right there. And so I could have defined metropolitan, micropolitan, and rural differently using one of like 9 different definitions. And so I used something called the MSA designation, which stands for the Metropolitan Statistical Area, which designates counties into either metropolitan, micropolitan, and all others which are rural. And so if these definitions, if I didn't use 1578, I used a different definition, I might have had different results. And so with all these papers right here, I work really hard to kind of address the issues that people have at the end here. And so I work hard to do this use of geostatistics for cancer research, food swamps. I like this article right here. This is an article related to, this is an old article that I had way back in the day, which talks about different definitions, geographical epidemiology, GIS, GPS, all the potential sources of error that you can run into when running geospatial analysis. You know, think of all the places where things can go wrong. And so I worked really hard to put a kind of a, you know, I've worked really hard to put all these resources, worked hard to put these resources here in one place. Most of these are my papers since I want you all to read them, but I also wanted to kind of, make you aware of the different types of papers out there. You know, most of these utilize statistics here. You know, I have means, medians, modes, standard deviations, all that other good stuff kind of sprinkled throughout here. So, you know, I've got, point values, all these other things here. And so hopefully you get an idea, just nice little summaries right here. Kind of pretty, pretty minimal right here. I've got z-scores, p-values. These are all things that you should hopefully kind of ring a bell. And so, well, I'll finish talking about the rest of these here, and then I'll talk about a couple of these other maps that I've got right here, and then we'll start talking about the final exam. So where I ended up, or where I finished up right here, was the idea of what we call multicollinearity. Basically, variables shouldn't be related to each other because they're basically going to cancel each other out. Other thing we have is what we call heteroscedasticity. And so it kind of looks like a cone right here, where basically as x increases, there's more, our residuals increase in y. Okay? And so some of these are really work, where that income increases, your household consumption on expenditures has more variability. And so you can see the people, over here who have high household income, but they also save a lot of money, where that people up here, they spend a lot of money here. Why? Some of these are going to be dependent upon the nature of the data, but the variability of data is not going to be consistent. So we call this heteroscedasticity. Other thing, we got the idea of the conceptualization and definition of neighborhoods. We did a whole exercise on this where you change the neighborhood. What's the definition of a neighbor? Definition of a neighbor. I'm getting real abstract here. What's a neighbor? Someone that's near you, right? What's the definition of near? Touches you? Borders you? It might be. Now, we could set those up. There was about 7 or 8 different definitions of neighbors that we could utilize. And so we talk about the different concepts of neighbors, where we look at distance. How far away are you? Adjacency. Is it next to something, or we have some type of interaction between each other? So these are all the different types of definitions of neighbors. If you're within a quarter mile of me, then you're my neighbor. If you touch me, if you're a state and you border me, you're my neighbor. Interaction, as you go further away from me, your impact is going to be less than if you're closer. And that's the concept behind IDW spatial interpolation. Meaning if I'm a point right here or cell right here, and we've got a temperature there, we've got a temperature way back there, we've got a temperature way back there, that temperature is going to have more of an impact on me in relation to the distance it's away from me. So it's basically a weighted average. Now, these aren't weighted average. We don't want to hand calculate even in Excel. And so we let the computer do it for us. And we just look at this nice created surface that we can go and extract points from. And so the idea of distance is that the magnitude of spatial separation, it typically works with Euclidean distance because, well, Euclidean distance is really easy to calculate using our distance formula. We can look at adjacencies, and so we can look at normal or binary equivalents of distance. So we can look at first and second and third order nearest neighbor. And then we can look at interaction where the strength of the relationship between entities is an inverse function of distance. So if Benjamin has a temperature of 72 and I'm a point right here, well, it's probably going to be 72 over here as opposed to anything else because that relationship between distance is going to impact this. You know, we're in a geography class, so place and space are going to matter. We have distance is not simple. And so all the different definitions of distance. So Cartesian distance, versus Pythagorean distance. So you can see here, this is the distance formula, but we know in reality, this is the flattened surface. So especially over longer distances, this distance is going to change over a great circle as opposed to flat distance. But we also have Manhattan distance, which is at right angles, distance through a network, time friction through networks, like stops and all these other things, because most of the time, when we talk about distance, this is what I care about. How long is it going to take me to get there? That's all I care about, right? That's all most of us care about. But this is, do you think temperature cares a lot about how far you need to drive? No. Okay. Or air quality cares about how far it needs to drive? No. And so be aware of the different type of phenomena that you're working with. Also, neighborhoods based on adjacency. And so we saw edges and corners, we've got corners, and so we also have these nice little hexagons. So we can use hexagons too. And if you take our crime analysis with GIS class that we're offering next semester, actually they break up, there's a tool in the crime analysis that runs like spatial joins and lattices all like in one function. I didn't even know this. I'm making you all create lattices and run spatial joins, and it could do it all here. But it also does hotspot analysis also at the same time. But I create these hexagons here. Why are these hexagons better than squares? Anyone know why a hexagon would be better than a square?
Are their centers closer?
Yeah, their centers are closer. So typically these hexagons approximate like surface areas better than squares. You know, these hexagons approximate surface areas better than square because they optimize the intersection of the points in a lattice. And I don't want to bore anyone too much, but if we had a set of points there, then if we had an equal lattice of points, basically if we created a hexagon, it would be the minimal, everything in this hexagon would be a minimal distance to this point versus this point versus this point versus this point. Okay. But in reality, this isn't, reality here. So you might see these pictures in like Dr. McGinn's like social geography or urban geography class, but we work with this once in a while when we create our lattices, but this is typically what we work with here. And we also have kind of second order neighbors where we have our first order and then our second order. And so when you look at all the different input parameters, this is what you'll look at. A couple other things we talk about here is that these are all the different neighborhoods that we deal with. And so, if I have a chance here, I kind of want to talk about the final a little bit more. But when we use different maps right here. We use the same phenomena and map hotspots differently. Using each of these, you're going to get a different set of hotspots. And so they have things out there called like how to lie with maps. Well, how to lie with spatial statistics. So something like contiguity edges only means it looks at the neighbor of the census block group that shares a neighbor where that inverse distance weighs the effect of the spatial relationship based upon how far away it is from that thing in question. And we talked about this also with spatial interpolation. So these are all the different ways that we can measure neighbor. What is your neighbor? What is far? What is high? What is low? And so people have done some really neat research in just how many hotspots am I going to have for this? What is the best type of neighborhood to use with crime analysis versus other types of analysis? And so I can run this here with these drop down here. I'm looking at my rate right here. And so neighborhood fixed distance band versus contiguity edges only. Same exact data. This is one type of hot spot, cold spot versus another type of hot spot, cold spot. Same exact data. I've changed one thing. Now, you noticed that last week, right? For the homework that you just turned in, didn't your values change a lot depending upon if you're using spline versus IDW? Did I ask you to do IDW squared or no? I don't think so. Spline versus Craig versus nearest neighbor versus IDW. And you saw some variation in these. Now, you didn't see a lot of variation in Durham because it was close to the temperature station, but some of these got really wacky really quickly. Didn't we run last week, one last week where it was like negative PM or something like that in the eastern part of the western part of the state? I forget. But we were getting some really weird negative PM values that we know don't exist, but computer doesn't know. But I thought this was really neat here. Look at these differences right here. Okay, the idea of interaction. Okay, this is what we kind of call a gravity model right here. This is basically how IDW runs. It has one value, another value in relation to the inverse of the distance. And so we have, how far it is going to be basically the weight. And we can square that weight if we wanted to, like IDW squared or second order, third order, fourth order, or whatever we want to do. And so these are going to have less of an interaction. And so there's really neat work on the idea of gravity models. Like, how do we model our behavior? That's, to me, I'm amazed at how we model our behavior and do these things. How do we model where I'm going to go shopping for shoes? People's livings, livelihoods are made out of these things there. Where are we going to build the next McDonald's? How much does it cost to build a McDonald's? A lot of money, a big investment. So if you get these things wrong, but when we talk about the idea of gravity models, this gravity is going to be the distance between two things right here. And when you're doing like sighting and all these other things, well, this distance is going to be very, very fickle in nature because you don't want things too close to each other, but you want them far enough away from each other where that it's going to have an impact. Okay, at what point in time are you going to drive to this store versus another store? What store, What are all the things? What makes you drive to one store versus another store to go shopping? Size of the store? Distance, a lot of it. Do you like the store or not? Does it have more offerings? There's a lot of things that go into that. But I think distance is a major player, right? And so within distance, and this is the whole idea of gravity model based on that universal gravity law or Newton or all that other stuff here. And so how attracted are people going to be to go to certain stores? Distance and size. And when we look at the gravity model, it's based on mass. So everything's going around the sun because it has such a tremendous mass. So what are we going to go to? And what store are we going to go to? How many of those stores are around? And so this is a previous student's work where we look at the attractiveness between a census block group and a farmer's market is a function of push factors and pull factors to driving time. And so what are all these push factors? What are all these pull factors? Have you talked about push factors and pull factors in intro class, intro to geography at some point in time? Yeah, push factors. What are things that are going to want to make you go somewhere, push you out of a place? Pull factors are things what are going to attract you to places. And so what we started to do is like we want to go to places where there's higher population, where there's more spending on fruits and vegetables. We want to go to farmers markets that have high variety of offerings, that have higher availability. I want to go to the farmers market that's always open in Greensboro as opposed to go to the strawberry farm that's only open on Sunday afternoons during summer. And so how do we quantify the variety of offerings and the availability? How do we attach these to numbers? And so we had a previous student who looked at push factors and pull factors where that, the spending on fruits and vegetables. People, we're looking at this place here. These places in blue, they spend more on fruits and vegetables. Isn't that where you're going to want to put more stuff there? People who spend more on fruits and vegetables, of course. Where do all the people live? The actually raw number of people live. So even though there's a lot of people who live down here, they don't spend a lot of money on fruits and vegetables. And so we created some of these, what we call gravity models. And this is kind of gets into some things with business analysis. And so we kind of created some of these drive sheds. We assigned farmers markets to different areas based on these gravity models as well. Last couple things I'll mention, statistical significance versus causation. Okay. And I think we looked at these before, where that this is the research that Dr. McGinn and I did, where that percent minority was related to by mail voting patterns, median household income, population density. They helped explain factors related to statistical significance, but do they cause it? Okay. Do they cause it? And these are some of the things that I saw was that statistics show that during times of high popsicle consumption, drownings are also high. Can we say popsicles cause drowning? No, they just occur at the same time. And so these things are related. Now, like I said before, we are the where people, or I'm the where people, where that correlation does not imply causation, but is a statistically significant relationship and is a good starting point to start looking at things. This is how they kind of started to figure out that, cigarettes caused lung cancer. And we're kind of got this day and age with the vaping. My kids, have gone through their vaping stages right now, and they don't really know what it causes because there hasn't been enough of what we call longitudinal study. Meaning that, after 20 years, this group of people were dying at like 10 times higher rate than people who didn't smoke of lung cancer. You think there's something related to those? Yeah. Now what's the jury out right now for vaping? The jury's still out. My kids swear there's nothing bad in vapes. There's nothing at all. They're good. They're good for me. Okay. All right, we'll see. I'm not sure what it's going to have. Now, is there something with vaping or groups of people who vape or whatever? Because a lot of times you'll see things like people who floss their teeth have lower rates of cancer. Or, what do you think? People, am I just going to start flossing my teeth every day, hoping I don't get cancer? What's the common thing with that?
Mouth cancer or anything?
I don't know. Maybe people who take care of their health via flossing their teeth do other things which decrease the amount of cancer. I don't know. This kind of gets out of my, skill set a little bit here. But to me, we start to look at longitudinal studies for some of this causation. So we can look at some of these factors. Why in minority counties or minority zip codes did we have lower by mail voting? Especially in the kind of minority majority counties out in northeastern North Carolina. Maybe they weren't provided with the resources to do that, or the population density, or median household income. Why did richer people mail in their ballots higher at higher rates. Why? Let's go ask a bunch of people at high income and figure out how or why, or they got the email or they got the mail where other low income neighborhoods didn't get that. I don't know. Yeah, and so these are good stopping points or dropping off points, and so that we can look at some of these issues with causation. Other thing we see is ecological fallacy. Relationships observed for groups don't necessarily hold true for individuals. And a lot of times we see these kind of assumptions, especially in this political climate, where that we can infer that aggregated data is true for individuals. And I've made this breakdown, and this is the paper that Dr. McGinn and I kind of wrote, where that if you see Democrat Republicans or rural Democrats had really low percentage of by mail, but really high COVID rates right here. You know, are we going to say that your friend who's a Democrat in a metropolitan area or even a rural area is more likely to get COVID than someone else who's not a Democrat? No. Okay, these are just very, very coarse descriptions for each of these here. And this is called ecological fallacy, where we kind of pass these down. And the last thing that we all love to do, people love to do in my house, where I know someone who fill in the blank. You know, I know someone who, didn't graduate high school and makes $200,000 a year. That's what my kids say. I know someone who, does this, and I'm like, well, the second you tell me I know someone who, what are you doing? You're proving my point. You know what I mean? You're proving my point right there. I know someone who drank all through high school and now they, own their own company or whatever. I got kids a little younger than you, so. So reaching a conclusion based on exceptional cases, and so we look at median household income or average weekly salary for someone with a master's, bachelor's, associate's degree, some college, no high school diploma, high school, no college, and no high school diploma. Do you really need a college degree if your friend who doesn't have a college degree makes $125,000 a year? What are you basically saying about this friend? They are the exception. The average person who doesn't have a college degree, we're looking at here, they make less than that, but they're just the exception. So we can look at a normal distribution of people here, and they just got a really high Z-score. And I get kind of really emotional about this because a lot of times, I always hear I know someone who, and, does anyone do that here? Anyone hear about this here? No.
Logical fallacies in general?
Yeah, logical fallacies in general. Exception, I call this the exception fallacy, where that I know someone who does this, where you kind of prove or disprove your point or whatever, and things like that.
I was wondering where like a trade degree would be on this chart.
To me, I'd probably put it somewhere at bachelor's. I have a kid who's 18, entered trade, making more money than I did 18. She's got health insurance, all that other good stuff. So I would probably put it right in the middle, right there with bachelor's degree. Yeah, I wholeheartedly promote that as well. But so things like this, because a lot of times we all, college is, stupid, or college is this or that. Well, what's your major and all these other things? If you're a, political science major, your major is going to be a lot different than your biology major and whatever else. Career opportunities and other things like that. But I get a bit emotional just from my side of things at my house when I hear, I know someone who, or what about this, or my kids, always kind of bring up these arguments. And I was like, you're proving my point here, kid. I know someone who got all C's in high school and then got, great grades in college. That's the exception. So that's about it from my end, all the things that we're talking about. So make sure you go through the class recording on this, and I will also post the recording on this as well. But the other thing I did want to talk about was the final exam here. And so I've talked about the readings right here. These are just the number of readings right here. These might give you some good ideas for your position paper. Okay. Down here, there's nothing with week 14. This is the final exam. So I've got a quadrant analysis example, and I've got a height versus weight table. So this is the final exam. I'll go back to this. And then I've got the position paper. So I've got the position paper. This is how you submit it. So it's due the 28th. I've got prior examples of some really good position papers that we have. This is the ArcGIS Pro template that had some data related to income, COVID, other things like that at the zip code level. You can go out and get your own stuff, do whatever you want. And then I've got a template right here, which is in Word, which has an interactive table of contents. So I already created the table of contents. So all you need to do is just go and update it, and it'll update that table of contents with page numbers and things like that. And so that's always really good to use, unless you know how to add page numbers and stuff like that yourself. I always like doing it, beforehand. And I've got the rubric right here for the 50-pointer. So hopefully my intention is that you use this as part of your master's thesis or master's project or PhD thesis or PhD dissertation or something like that. Just use some of the methods and kind of build upon this. That's what I would really, really hope. So real quick, we're going to look at the final exam, and I'm going to try to get us out of here by 7 or so. And so I've got an Excel spreadsheet that I can download right here. Let's download it. Okay, so I got an Excel spreadsheet right here. And then I got another Excel spreadsheet where I am modeling height versus where I'm modeling height versus weight using information from using an equation. And you'll see what these things look like here. Okay. So, okay, it looks like I've got a new form. Okay. All right, so I ran some quadrant analysis right here. Observed, okay. Expected. All right. Looks like I've got everything right here. I went through and run the spatial joins and statistics on everything here. So I've got these up and ready to go. So when I click on modules right here, I'll post the directions for this later this week, but the expectation is that I'll give you a password. You'll take it during class this time next week. You'll take it during class, and then those of you who are taking this class as an online class, I'll give you a time period of probably 3 or 4 days to take it. So here's the final exam. Click on preview right here. All right, let's see what we got here. All right, reaching a conclusion that goes against what your data dictates based on atypical cases we just talked about. That's probably the first thing I thought about. Usually I deal with this with my kids. The what about, or I know someone who, or whatever, when I go to prove a point or whatever. I got this one here. In the first few, we'll talk about some of these atypical issues here. Some of these might be reworded a little bit. So if I have time and energy, I might reword some of these or look at these a little different. So you got a good idea of what we're looking at here. When performing geostatistical analysis, I find patterns and clusters when analyzed at one scale that do not yield the same patterns at a finer scale. Okay, what is that referred to as? Okay, I am running quadrant analysis and created a fishnet for the entire study area. These are really long questions, I noticed, making you think today or next week. Okay, so, and you notice I ran a lot of these, and a lot of these are going to be the interpretation of, results. And so between quadrants in green and the deer vehicles, however, some of the quadrants extend outside of the study area and do not spatially coincide. In this example, I may run into errors because, now you notice up here, if I run quadrant analysis with these green ones at the edge, what are the problems that I'm going to run into? I run a spatial join, and guess what? There's only one. There's only one. There's only one. This really isn't truly a quadrant. Really, is it? It's only like a third of a quadrant here, or a quarter of a quadrant, or a tenth of a quadrant right here. Now, what did we do in class? Does anyone remember what we did to circumvent that? This was a long time ago, but when we ran the quadrant analysis, I picked only the quadrants that were entirely within the county, right? So it didn't include this or this or this or this or this. It only included the ones that were entirely within the county, because that's a spatial relationship that exists. We have intersect, we have entirely within, so that we don't have to address issues of what we call the answer. Okay, one of these is the answer. I was going to say it, huh? In running correlation and regression, the value we're trying to predict is called what, using one or more what. Okay, that should be pretty straightforward. When performing GIS analysis, we might find that regions with more people tend to have higher counts than regions with lower populations. The process of what? This is what we did kind of at the beginning of class. When performing geostatistical analysis on a data set, we may get data from one part of the region using a particular set of methods and another from another set of methods. What is this called? So if I'm getting the Durham City Police Department data versus the Sheriff's Department databases that were collected using different methods, collected using different attributes, it's probably not a good idea to mix and match or combine them for the entire county, even though it might look nice and pretty. That's the sad thing about everything, is that it looks pretty cool for an entire county, but it's not going to be spatially or temporally contiguous. And I think it's really, dishonest is probably too strong of a term, but it's not going to be telling. Explain the difference between a local and a global statistic. To measure spatial autocorrelation. And so that big fancy word, spatial autocorrelation, is just the degree to which high features are near high features, low features are near low features. And so we talk about things like Moran's eye, local Moran's eye. Local Moran's eye is something a little special, but Moran's eye, we had Geddes Ord, we had hot spots, we had kernel analysis. We talked about a half a dozen of these metrics here that describe spatial autocorrelation. I wish to run quadrant analysis for this set of points for an entire county to see how it compares. Okay, so deer vehicle collisions for an entire county using the formula we discussed in class. If there are 934 deer vehicle collisions for an area of 657 square miles, compute the area of each quadrant length in miles. The units should be in miles. Remember that big fancy equation? Because someone's probably asked right here, like, who died and made these quadrants this size? Who decided that? Why don't I just make like 4 quadrants and just count them all within there using my spatial join and my summarized statistic? Why are they this size? I calculated using one nice little formula that we talked about in about week 7 that gave me the optimum size. And it was like the square root of 2 times L over N, or 2 times A over N, right? Look it up. Okay, but there's a formula in there. And that will give you the size of it where you plug in the number of features, the area, you multiply 1 times 2, one of them times 2, and divide by N and take the square root of the whole thing. Because when we make quadrants, do we want the quadrants to be really big? Not really. Why? Because if I only have 4 quadrants right here, well, it doesn't really show spatial variation. It just shows 4 of them right there. I don't want them all really small because I'm going to get a lot of 0 values. And so that formula is derived so that I've got enough values that have some 0s, have some 1s. It might go up to 6 or so. And so I've got a formula right there that you're going to look up and use and kind of plop in there.
It's going to be open note.
It's open note, open book, open anything. Yes. Just not open person. Okay. So you can utilize your books, your notes, whatever you want, videos, or whatever you got. Just make sure, and like I encourage everyone, is make sure you know where these resources are found. So I was talking about this formula. You know, if you don't look for the formula until Friday or next Wednesday at this time, that's on you. You know what I mean? Go look up the formula now and know how to utilize it. You know, plug that thing in. Because you know what? I might go and change these numbers right here. So I wouldn't write down 934 and 657.7. I might change those. Not might, I probably will. Okay. Compute the area of each quadrant. So if I know the length of something is 2 miles, what's the area of it? 2 times 2, which is 4. Okay. If I were to increase the size of the study area, but the number of vehicles remain the same, number of collisions remain the same, what would happen to the quadrant size? So if I got that formula in there, square root of 2 times a over n, what happens if that n increases? What happens if the denominator increases on something? If I go from 1/2 to 1/3 to 1/4 to 1/5 to 1/10, it goes down. And then I ask kind of another question here. Now, what you can see right here is I ran a spatial join, summarize, and basically what I did right here is I ran this quadrant example right here. You can see it right here, 56. And so you're going to use the formula to find the expected proportion right here and the expected number of grids. Okay, so what you're going to do is use this. I already did everything. I already used the 956 and all that other good stuff right there, the observed number of grids. And I ran the spatial join. I also put in that little number right there. So given this gamma thing here, okay, and there's a little formula right here called Poisson distribution here. And so I've got an expected. This is what I've got observed. And what we're going to do is we're going to create a Kolmogorov-Smirnov curve, a big fancy word for just a line graph that's compared to the other line graph. This shows me what it is. So you're going to use that formula from quadrant analysis right here. Okay. So what did you get for A? What did you get for B? What did you get for C? And what did you get for D? And what did you get for E? That's all you're gonna. Now I created the graph, the expected versus the observed. So I ran this. What'd you get? What does this tell you? Is it close? Not close? Do we want it to be close? Okay, so when we get something, I ran the expected versus the observed. I went through and ran it all for you. You just got to do a little Excel calculation for me. What's this tell us? I ran set of points, deer vehicle collisions for Rockingham County, listed first, and then Guilford County listed second. So you can see this one's called Guilford, this one's called Rockingham. How is the nearest neighbor calculated? Ooh, explain to me how the nearest neighbor is calculated. And then using the diagram, which of the following counties has the most clustering using the nearest neighbor, Z-car, Z-scores, and p-values?
This is all fiction, but it doesn't look like we'll be actually using ArcGIS.
No, I don't think there's any ArcGIS. I just kind of output the results here. Okay, I threw a little Excel in there, but that's about it. Okay. And if you wanted to, I'd open up ArcGIS Pro because you can go and run the local Moran's Eye, so you can type in the tool. How does this tool work? What are the input parameters? So I do have a couple things here. If you were to run Ansel and local Moran's Eye, okay, you would see a low high. What does low high mean? So maybe Google Ansel and local Moran's Eye, Google it, see what it looks like. And so you can see low, low, high, high, all these other things here. This is for average family size. When running cluster analysis, the issues of different neighborhoods arise. Give me 3 different types of neighborhoods. This is worth 6 points. Okay. Oh, according to the World Health Organization, height can be predicted by one's weight using the equation of weight equals 3.966783 times height minus 124.691. So if someone's 65 inches tall, their predicted weight is 133.1499. So what is the predicted weight of someone who is 62 inches tall? Look what I have right here. Okay, so I have a nice little graph right here. I have an independent variable. I have a dependent variable. Okay, and I can just type in a nice little equation where that your predicted weight is equal to a product of what? Your height times something minus something else. So that now I have sample one. I have these people here who are 56 inches tall, 105 pounds. But according to the World Health Organization, I can plug in their weight and figure out person one, person two, person three, person four, how much different they are than their predicted weight. So I ask you, what's your predicted? What's your predicted versus your actual? Because you can see these two people right here, one's 58 inches, one's 60 inches, but they both weigh the same. So obviously they're not going to fall right on that line right there. And so what I ask here is, I like these questions here, meaning what's the predicted weight for someone who's 62 inches tall? You could plug it into the equation. I also give you an Excel spreadsheet so that you can basically calculate those for everything. According to this equation, someone who weighs 160.91378 pounds should be how tall? And then I have this table, residual equals actual minus predicted. Okay, which person has the highest positive residual? Basically meaning they weigh more, their actual is more than their predicted. They weigh more than what we would predict them for. And then what do you think the other question is? Which has the highest negative residual? So when you make that calculation for residual, what's the highest negative mean? Is negative 24 higher than negative 10? Yes. Okay, the biggest difference. I got into some arguments to the death last semester on this one here.
What highest negative means?
Yes, highest negative.
And it's the biggest number.
The biggest negative number, or the smallest number out of all
The
those.
largest negative magnitude.
Largest negative magnitude, what he said. Largest negative magnitude, yes. Furthest away from zero. Okay. Basically meaning we can't predict, their actual is much smaller than their predicted. And so when we run this graph, is it a positive or negative correlation? Which of the following best describes spatially weighted regression? One question on my talk earlier today, and it basically means that we create our own brand new R squared with every single enumeration unit. So you can see that map for the southeastern United States. Each had differing R squareds, where that we run it for OLS, we get one R squared for the entire, for all of the counties. So location is going to also be part of that y equals mx plus b. I'm running single factor regression. What do I have here? Diabetes death rates can be explained. What do I have here? What do I care about a lot? Okay, R squared, joint R squared. What am I looking at here? Okay, I'm looking to see if there's a relationship between COVID and diabetes. Okay, what are the things when I run this output, what do I care about? Okay, so make sure you look at this. Look at this R squared, really small R squared. That's going to be a good indicator. Okay, so what does this tell us here? What does this tell us here? Is there a relationship between by mail and COVID rates? Okay. And then how can I explain these? I run an ANOVA right here. What does this ANOVA tell me? I ran an ANOVA to see if there was a difference between metropolitan, micropolitan, and rural percentage of unaffiliated voters. Okay. And so in metropolitan regions, it's 32% independent. Micropolitan is 31%. In rural, it's 29%. Okay. And so is that equal? Is it the same? Are they statistically different? And basically, an ANOVA is when you run a two-tailed t-test for more than two groups. And all it tells me is that they are different. Or maybe they're different. You tell me if they're different. But my null hypothesis is that the independent rates for metropolitan is the same as micropolitan is the same as rural. And so what do these results tell me? Is that true or is that false? Or I can't prove that it's true. One of these is the right answer. This is with interpolation. I talk about different types of interpolation, default settings, and then finally my good old two-tailed t-test right here. So what is these two-tailed t-tests? Now, to be honest with you, in these two-tailed t-tests in ANOVA, some of them, they might not be proven. So they're not going to all be proven. Okay? Because not proving something is different is just as good as saying that they're the same. We can't prove those with statistical significance. And so you can see the point values. There's 34 questions here. So each of them about worth probably 2 to 4 or 5 points. But you can see some of these go up to 6 or whatever. And so I've got some 2-pointers here, especially some of these that cascade upon each other. So if you get one question wrong, I don't want you getting like 6 points off for each one. So for some of these graphs. And then you can see these here. So it's about 7 o'clock. Are there any questions for me here?
I know small, but
Okay. Well, we feel good. Barbara, Michael, Caitlin, Chantel's still, Chantel's still there. Any questions?
Yes, how many questions are the exam?
34.
Okay.
Yeah, it's about 34, 35. I might add a couple this week. And so this is what I gave last year. So you're not going to see these exact samely worded questions. You might see slightly different answers. So don't go put A, B, or 797 divided by, please don't, because you're going to get the wrong answer, I guarantee. About 34. I might, if I think of something during the week, I might replace them, but there'll be about 34, 35 questions. No GIS, just a couple of Excel spreadsheets that I provide for your use. And like I said before, download the spreadsheets. Download the spreadsheets, do the Poisson, distributions before you even come in. So practice doing the Poisson distribution, because I might have you do a slightly different gamma value, but if you know how to do the Poisson distribution, you're good to go. All right, that's about it for me here. I'll stop recording right now. And so all of you kind of joining us online or asynchronously, good luck on the exam. I'll post the kind of guidelines and routine for taking it, and good luck.
For my position paper, do you want to know what I'm doing it on, or do you want me to